Hi everyone, my name is Hyun, and today we're going to discuss about the strategy pattern, which in short it is a behavior design pattern, which it enables selecting algorithms at runtime. So before diving into the details and learn why do we have to use it and how do we use it, I will walk you through some of the basic terms and knowledges that we've learned in our class. Okay, so we have abstractions, which focus on what the objects can do, not how they do it. We've learned about encapsulations, of which we hide the inner working of an object. We hide all the data, the unnecessary details, and only show what's necessary, like some methods or some of the attributes. And we've learned about polymorphism, which the objects can take on different forms or behaviors. And we've learned the most important is the concepts of inheritance, which is create new objects based on existing one, inheriting their traits and behavior, enable code reuse, right? But understand all these basics is not enough for a good, software designer or system designers, because we have a lot more to learn. And so the first design patterns when I used is the strategy pattern, which the former definitions, kind of long, like defines a family of algorithms, encapsulating each one and make them interchangeable. And it lets the algorithm vary independently from clients that used it. So you will understand each of these one, after I break it down into some design principle presented. And you will learn, okay, what is the family of algorithms? What is encapsulate each one and make them interchangeable, and how do you make it independently from clients that use this algorithms packed. And so, okay, let's jump into our first design principle, which encapsulates what varies. So imagine we have a duck class here, right? So we want to implement the flying behaviors and we want to implement the quack behavior. But if rely solely on inheritance, right? So if you want to make a super class of a duck, and we inherit all the other ducks, the class like RoboDuck or a mother duck or any other types of duck will inherit it from superclass duck. And when we want to add a new features like flying behaviors, so all the other ducks that inherit from it will be able to fly, which is really great, right, for code reuse. But imagine that we have a rubber duck like this. So the rubber duck cannot fly. And also I've removed the squeaky sound so it cannot squeak either. So if we use the superclass duck to implement our methods, this one will be wrong. And there's one way to fix it, which is we're gonna methods overloaded. We're gonna override the methods, and make it okay, not making any sounds, or make it not flying anyway, not making it flyable, right? But imagine when this is for the design purpose. What if I ask you to change the behavior of this duck later on? And what if I ask you to change this for 100 types of ducks? Like, what if we have 100 types of duck and you have to manually doing all of that? And so that's very tedious jobs to do. So the idea is that we pull out what varies, what might be changing in the superclass, right? Like in this example, we have the duck class. It has the flying behaviors and quacking behavior. It is varies from each other types of duck. So we pull it out and we're gonna implement here. We're gonna implement all the behaviors, and then we're gonna put it back to the duck class. And how do we use it? Now let's just think of, okay, we're gonna pull it out, we're gonna do something magical here, duck behaviors, and then it's gonna act based on these behaviors. And okay, that is encapsulate what varies, text what will be changing, and pull it out, implement it based on the other class, right? So the second uh, principle is program to an interface, not an implementation. What it does, right? So what does it mean, an interface and an implementation? Program to an interface, not program to an implementation. Okay, so I have an example here, which called it interface, right? So I'm gonna put this side by side for easier to view. So as you can see here on the screens, I have a class animal, right? I have a dog and a cat and a cat. The dog is an animal and a cat is an animal, right? It inherited from the animals. So the animal is an interface, what it does to program to an interface. So take an example when I program to an implementation. I can create a dog, a dog objects, right? And when I want to when I want the dog to make some sound, I will have to call, okay, dog, you will have to bark, right? You have to bark for me. And let's see, okay, so it also called woof woof. I can do the same for the cat, which I can make some sound for woof woof and meow, right? So that is programmed to an implementation. But when we want to program to an interface, so we can make like an animal, which this animal is a dog, it should be saying backward. A dog is an animal, right? So this animal holding this dog here, right? And when we implemented the make sounds here, right? We implemented the make sounds in each of the class here, right? So this is called program to an interface because we are talking through a middleman here, which is not exactly a middleman, but you get the idea. That is, okay, I call the animals and I call the make sound methods from the animals. So the animal doesn't care about, okay, how the dog is making a sound, how a cat is making a sound. The only thing that it knows, that is that animals can make a sound. So it will make one sound, right? So I can, okay, new cat here, I can change the cat for the dog, and it's happening the same. It will meow, right? It will make some sound based on, the method that animals. So this is the concept of polymorphisms that we've learned. But this one will enable, if we can take this further, right? By, kind of like implement like a get animal methods somewhere in our code, and this get animals will return like a dog objects or a new cat objects, right? So the animal doesn't care, you know, the animal doesn't care about, okay, what the types of animal is. It just receives, okay, this is an animals, and it will make some sounds when we require to do so. So this enable to change the algorithms in runtime, right? So take another examples when I have a players here, right? A player it has the player has a weapon, and the weapon can be an interface, right? I don't know how the weapon will work, but I know that, okay, when I perform attack, the weapon will act accordingly. So here I have an interface of a weapons, and so if I want to shoot a long range, I can make a bow, right? For long range shootings that inherit from this, and I can also do, okay, the attack here, and so when it perform attack, we will call the bow. How it will shoot. It will shoot long range. It will, shoot an arrows. Or I can make it a sword, which it will attack. On a near distance, right? Uh, that melee attacked. And I can adding another weapons like I have a staff, right? I have a magical weapons, some sort of things like that. And so if you cast a spell, based on the attribute of the staff here, but the player here doesn't need to implement any of these, right? the player doesn't need to implement any of these. It only knows that through the weapon interface here, through the weapon interface, it can perform uh, the attack actions. And so that is the core ideas of program to an interface, not an implementations. So let's come to the third design principle, which the first one we take what varies and we encapsulate it, and then we implement it, through an interface. Here we have the flying behaviors. We have various flying behaviors like flying with wings, no flying at all, or fly with a rocket, which, yeah, that's weird, but the behaviors, it varies. And we program to an interface to call from the interface from the flying behaviors here. And the third one, we composed it into one. So here, as you can see it, the duck, the duck, which is here the client, the duck class, it has a, it is a relationship of has a fly behavior. It has a fly behavior that it cannot fly, fly no way. It has a fly no way behavior, and it has a squeak behavior, right? So this relationships here is called compositions because it is composed of many other, you know, isolated independently from each other. All of the classes are independently from the clients, right? So this one can fly with a wing, or it cannot fly, or it can fly with a rocket. And also the same for the quack behavior, which it can compose of a squeak behavior or a mute quack, which it has no sound at all. So the client can make use of here, encapsulated family of algorithms for flying and quacking. So the family of algorithms here, you can see the fly behavior is a family of algorithms. Fly with wings, fly away, fly blah, 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 many other fly behaviors. And so that is compositions of inheritance, because when you favor compositions, you can change the components. Like a chef, you cooked with these ingredients, and you can, okay, change with the other ingredients. You can add more sauce. You can change this, change that. But when you inherit from it, it's gonna take that, and it will be, it will be hard to change, or I think it's mostly impossible to change at runtime. And so, to sum up the strategy pattern, um, let's read again the formal definitions. The strategy pattern defines a family of algorithms. It encapsulates each one and make them interchangeable. And the strategy lets the algorithm vary independently from clients that used it. And so when you look at these diagrams here, you should be able to understand, okay, what the strategy does. So we've learned about three design principle, encapsulates what varies, and we implement to an interface when we pull it out, and then we composed it back to our superclass here, which is the fly behaviors and the quack behavior, with a has a relationship, right? So this one is a because a dog is an animal, is a animal. The cat is a animal. But the duck, it has a fly no way behavior. The duck has fly with wings behavior, right? It also has a quack, a squeak behavior, it has a quack behavior, right? So bear in mind too that when we learned about relationships between all of the types. And so the applicabilities of these is when we want to switch between different variants of an algorithms at runtime. So I will talk about this later when I have a rubber duck. At first it will be initialized with it flying away because a rubber duck cannot fly, right? But um, when I added a rocket to it, say I added a rocket to this, and then I make it fly, right? So that will change at runtime when my code is running, right? And or when you will apply this when we have lots of similar classes like this, like we fly with wings, we fly with rockets. It's all about flying, and it's similar. Yeah, it's similar to each other. You have lots of it, and when you want to avoid exposing the complex algorithm-specific data structures, you can also use it to hide the complexities of your code, right? You only need to, okay, the fly behavior, you can implement a lot of things down here. Can, make a rocket and many other things, but you will hide the complexities and only include, okay, a fly behavior and perform it. That's it. And that in the fourth point is when you have a massive conditional statement. This one, to be honest, it will be hard to explain, but think of like when you have a large conditional, like, okay, is it a real duck? No, so it cannot this. Is it made out of rubber? Yes, so it will have a behavior of this. So, the hierarchical condition will continue to go on, further and further and further until you reach the final destinations, which is the whole trees, like the whole conditionals graph, something like that, just to get into the endpoint to see which behavior should be done. And so you want to reduce that. You want to replace that by using this strategy patterns. And so let's apply this into our rubber duck example by implementing this whole, set of diagrams, right? And so let's see. I've already have a duck here, and I'm gonna put this to the right side for easier to see. And okay, so I've added all the necessary libraries. So first, I'm gonna code an implementation, right? Sorry, an interface, which is the fly behavior here. It has the um, fly, you know, interface, virtual void fly. And okay, so I'm gonna implement all of the methods, all of the behaviors here. So the first behavior is fly with wing. It's gonna inherit from the fly behavior. Okay, so it's gonna fly and fly away. So for the behavior that it cannot fly. So we also do the same for the quack behavior. So here we have the quack, right? The quack here, the quack will quack. Or we have mute quack, which will be silent. Or we have the squeaks for this little dude, the duck. And the duck will squeaks whenever we pushed it. But currently it cannot. And also we have our parent class, or we have our super class, which is our duck. Our duck has a, fly behavior and has a quack behavior. This is compositions. It is not inheritance. See, it is a compositions of fly behaviors and quack behavior, right? And we will, make a perform fly to call the fly methods from that interface. This is programmed to an interface, not to an implementation. This also does. But the swim here is, all ducks float, even decoys. So this one is not varies from other ducks because every duck can float, right? So it is the same, it stays the same. So we state it here. And we also enable this strategy pattern. This strategy pattern only works with, no, not only works, but it will be best if we can, utilize it to change the behavior at runtime. So at runtime, we can set the behavior by, adding this two line of code. Like we set the behavior, set back behavior, and set back the quack behaviors here. So this one will enable to change the behavior at runtime. So let's just only focus on our model ducks here. So the model ducks here, as you can see, it's not here. But anyways, the model duck will inherit from the public duck, which here it will contains all the necessary, inherit. And then we're going to initialize it with fly no way because a model duck cannot fly, but it can quack. So we set the quack behavior of it, when we initialize this model duck. And I'm going to add some display, just clarifications. And let's just run this code first before we explain more code. And so when we learned about the model duck, right? So here, the first line, we initialize duck models with a new model duck. And we're gonna perform the fly on the second line here. And okay, so it cannot fly. Here it cannot fly because the model duck is initialized with fly no way class, right? So when I tell the models to perform fly, it cannot. But at runtime, here at runtime, I'm setting the behavior of this model duck by set behavior, by, this fly rocket power, which I will equip this model with the able to fly with a rocket, right? So how do I implement it? So we simply need to inherit from the fly behaviors here. We implement through the fly behavior interface. We create fly rocket powered, and we implement the fly methods here. Then we set the behavior. So when we call again the perform fly on the same models here on this line. Here it's saying, okay, I'm flying with a rocket. And that is how ladies and gentlemen, we set the fly behaviors at runtime. And okay, so it can perform some quacking here because the quack hasn't changed from the initializations. And also we call the swim method, um, which that's it. I think that's it. So congratulations all on your first design principle, which is the strategy principle. And I hope that you will grab some of the knowledge of the essence of this design patterns to apply to your code. And yeah, that's it.